Hey, this is Dr. B, and let's solve some gas law problems. These are the problems of Boyle's, Charles, and Gay-Lussac's, which means we're dealing with pressure, volume, and temperature, for which this little ditty might be helpful. Boyle, the VP, that's volume and pressure, saw Charles watch TV in Gay-Lussac's TP. And there's an image to help you remember this little poem, and that should remind you that Boyle's law is about volume versus pressure, notably P1V1 equals P2V2. Charles is watching television, so temperature and volume are related there. And Gay-Lussac's law is all about temperature and pressure, the dangerous law. This is the only one that's inverted, therefore it's P1V1 equals P2V2. The other one are proportional. As temperature increases, volume increases, and as temperature increases, pressure will increase if the system is not expandable. Therefore, those are written as T1 over V1 equals T2 over V2, and the same kind of relationship for Gay-Lussac's. Okay, that's the basic idea. Let's go ahead and solve some problems. As we read it, we will replace these data pieces with letters, right? In this case, that's a volume. A 0.4 liter engine, that's our initial volume. At 2 atmospheres of pressure, that's our initial pressure. Increases tenfold to 20 atmospheres. What's going to happen to the volume? Well, it's inverted. If the pressure goes up 10 times, the volume must go down 10 times. The answer will be 0.04 liters. And we solve it mathematically by plugging in. I don't believe I rearrange, but it's usually better if you do so. So let's just fill it in. Solve it. Cancel your units. We get the same answer. Here's a Charles law problem. We have a 2-liter balloon. That must be our initial volume. We're heating it up. The temperature goes from 25 to 323. Wow, it looks like it's increasing 4, 8, 12, almost 13 times. Nuh-uh. Because we have to change from Celsius to Kelvin. And look, we're going from 298. We add 273 to each one. 2596. Yes, I chose that on purpose because, in fact, it's only doubling. If the temperature's doubling, the volume should double if it can expand without any resistance like that. The final answer should be 4 liters. I'm sorry, 4 liters. Yes. What will be the final volume? Not atmospheres. That's a pressure. So we should change that to liters. There it is. Plug it in. Cross multiply. Solve for x. And we get a 4-liter final volume just like we did in our head. One more. We got a closed fixed volume aluminum can, so it cannot expand or contract. It's got some air in it. It's at 4 atmospheres. Let's call that our initial pressure. Somehow I'm calling it the final pressure. Oh yeah, I can handle the pressure. Sure, we can do it that way. You don't have to. Of 4 atmospheres before it bursts. If this closed 2-liter can, that's our initial volume, but it can't expand, so you're going to find that that doesn't matter. As at 1.2 atmospheres, finally we have an initial pressure. And we heat it from 25 to 100. Once again, we should remember always to use Kelvin. So the temperature is not even doubling. This thing is not going to burst. That's what they're asking. Will it burst? No, I don't even think it's going to hit about 2 atmospheres, well below the busting point. So if you were in a hurry, you could just say no, and you could explain your reasoning, or you could be quantitative about it by setting up the problem. First, write the formula. Replace those little letters with numbers that have units as well. Cross multiply, solve for x. And we see that as predicted, it didn't get anywhere near 4 atmospheres. And so that tank, that aluminum can, would not burst. These are 3 gas law problems.